Welcome and thank you for joining us for our webinar, Must-Haves for High Availability of OpenStack Networks. This webinar is part of our Tales from the Front Line series, where we're bringing our professional services front and center to talk to you about what they're seeing in the field. I would like to start off with a bit of housekeeping. First of all of our guests will be muted throughout the session. You can go ahead and use the Q&A window to ask questions, and we've saved some time at the end to go over those questions and answer them live. So without further ado, I'd like to introduce our host, Julian Neitz, our Solutions Engineer at PlumGrid. Over to you, Julian.
Thank you, Deborah. Hello, everyone, to the webinar where I am hoping to show you guys some tricks and some lessons learned from the field deploying highly available OpenStack networks in the field. My name is Julian Neitz, as Deborah said. Quick word about me. I've been a solutions engineer for the professional services team at PlumGrid for about a year now. I've been actively working with OpenStack since the Folsom release, so it's since like late 2012. Before PlumGrid, I worked for the middleware and the cloud team at Red Hat, and also did some DevOps consulting on my own. And I'm currently involved in the design, prototyping, deployment, and integration of custom software-defined network solutions for our clients. So without further ado, let's see what we're going to be talking about. So I thought I should start with a quick introduction and brief history of the networking stack that we get with OpenStack. See, where we are and how we got there to better understand, why things work the way they are right now. And then we will look into the new developments that are enabling companies like mine to provide software-defined networking for the OpenStack clients and operators. And then we'll go over some requirements, or basically we'll see what is needed to achieve high availability, and obviously we will share how we do it, like on our side, how we achieve that. And I've also prepared a quick demonstration of all the theory that we were talking about. I will show it on a live setup, which is highly available, and we will be able to see how things fell over and keep working. And after that, we will open for a quick question and answer session. So let's start it. So historically, the three main components that we get in any data center that's in operation are compute, storage, and networking. That's like the basic ABC of everything. With the advent of virtualization, compute was the first one to get like a really nice chunk of functionality added to it. A lot of people worked on getting compute and consequently storage functions, getting virtualized. A lot of products came out, and they've been out for a long time. And actually, networking was the one that sort of played the catch-up with the virtualization trend. The fact that all of the hardware networking appliances vendors didn't really want to lose lucrative business played, a big role in that because, the way they were implementing, network functionality was, even based on standards, everybody did their own little, twist on things. And, vendor lock-in as a result was like a big thing that was, kind of in a way of how like everything else in the data center was evolving. So as OpenStack was introduced and grew in popularity, many things started to change, like as a result of these progresses that we, these strides that we made in compute and storage, the first OpenStack sub-projects that utilized them kind of got the chance to get everything right, with the first go. Like nothing has been changed dramatically as the networking has. So like the first sub-project of OpenStack that dealt with networking that came out of, the very first releases was Neutron Network. Neutron Network implemented a very simplistic and easy to understand and use way of implementing network functionality and network topologies. And in fact, it was so easy that it's kind of still around. I mean, efforts were made to deprecate Neutron Network in earlier releases, but actually many people were still using it in production because, it just gave, simplicity and easy maintenance. I would assume if your deployment was, straightforward and it didn't have like many nodes, it was a very, very good choice to go with. So with that said, networking in general plays a critical role as it's tasked to deliver both isolation and connectivity at the same time of all the elements that comprise OpenStack. You want the VMs that you spin up or the containers that you spin up to either talk to each other or to be inaccessible from different points. And it also at the same time it has to facilitate and not be in the way of communication with the compute and storage part of things. So as a result, there has been quite a bit of development into that area, and with the Neutron Network being the lay of the land with the first releases, there were like two ways of doing networking that kind of stuck. So the first one was with Neutron Network, you can easily and efficiently create a flat network, for your OpenStack. Basically, if you guys see the diagram, everything is like on untagged interfaces, and basically you are allowing your hardware to do all of the switching and bridging and everything. So, yes, it doesn't give you much flexibility, but, again, very straightforward. So as a result, the VM interfaces in a setup like that are all bridged to a network adapter, which is fine for a single tenant. The thing is though, like you didn't get any layer 2 isolation. You didn't get multi-tenancy. You couldn't get like overlapping IP address space. And for layer 3, the first hop routing is either by your physical network, is achieved by your physical network, or you can achieve it with the L3 service in OpenStack. So meanwhile, like while people were using that, Neutron was introduced, and starting with the release, and it was designed from the ground up. It was designed to offer modularity and to be basically an abstraction layer on top of different networking backends. So with the introduction of Neutron, another model was available. So technically, this VLAN networking model is also available for Nova Compute, for installations that use Nova Compute. But with Neutron, that was like deploying this kind of topology was easier. So as the diagram states, like you would get a trunk interface coming into your compute nodes, and on that trunk interface, you can carve as many VLANs as you need for your tenants, and as a result, you would get one VLAN per tenant, and you'll get multi-tenancy. You will get layer 2 isolation and overlapping IP address space. The VLANs themselves can be either pre-configured on your physical switches, or through Neutron, through like switch plugins that vendors will give you to use, where you can automatically provision those VLANs on your hardware. And with the VLAN model, layer 3 first hop routing is either via your switches or through your L3 service in OpenStack. So as a result, again, of all that progress, people were trying to, well, the developers decided to phase out Nova Network in the Havana release, but that was like a decision that was like an attempt that didn't succeed, and because again, still many users were running it in production. And Nova Network is in fact still available in Juno, and the patches are being accepted and merged into the main branch. So what I'd like to do is actually concentrate a little bit on Neutron, because this is what enables us and our clients to achieve like a solid high availability for our networking. So Neutron matured very nicely over time, and actually there isn't like any major new feature that is expected to be merged into its main code in the future. It's basically very solid and very mature project. So some of the characteristics of Neutron are that it provides a network as a service. That is, it allows both operators and tenants in your cloud to orchestrate their network topologies. You as a tenant can create a network and even remove it as well. It's like that is one of the multi-tenancies that it enables, which is a great thing. It provides through Neutron API calls. You can provide external connectivity. You can create a external network to connect your instances, your VMs, or whatever you have to the outside world. You can interconnect networks. That is, you can create routers between your networks. You can create multi-tenant networks that have their own private, IP space. You can also obviously connect workloads to each network. You can attach VMs that will do the work for you. And so it is an abstraction layer. It has like a modular design that allows for plugins to be created for it. And as I was saying earlier, like many hardware vendors would provide you with their plugin that will interface with their hardware, be it Arista or Cumulus. You guys get the picture. So it exposes vendor-specific network virtualization and SDN technologies to the end user, which is, again, a fantastic thing. As it is, as I said, it's a front end to the back end that implements your network functionality. And one great functionality of Neutron, one great thing about it is when you integrate it with an SDN solution, it has and it will pass through any API calls that have to do with the lifecycle of your network topology, to pass them through to your SDN. It does not implement any, anything out of the box. You have to provide Neutron with your backend. Like it's not going to go and create a network for you until you tell it, what backend to use. And as a result, it can be like a very thin or very thick thing. Like it really depends on what your backend is. Originally, out of the box, with most of the OpenStack distributions, you get a setup that is, it works fairly well. With the, if you have like a small amount of tenants, it's not a problem. You get an ML2 plugin with OVS, and actually I will go into that in a second, which people usually think this is the default that you get, and that's your normal operation, but that is not the case. It's just a convenience provided by one of your distribution, basically. So I'll come back into that in a second, but I want to have like a quick word on Neutron plugins. And actually, before that, what Neutron provides is like the great thing that we can get using Neutron with its plugins and sub-projects is we can get an overlay-based networking model, to contrast with the flat and the VLAN-based model. You can get an overlay, for your network that will give you, like, for example, if you were to use a VLAN model, like you're limited to 4,000, less than 4,000 different VLANs. If your installation is big, you'll run out of VLAN IDs pretty quickly. So with an overlay-based model, you get like a lot more. You can create a lot more VLANs. It's based on a technology that allows for that. It can be GRE, or it can be like in our case VXLAN. And basically, in your overlay-based networking model, the overlaying MAC in IP tunnels that you create, they're like depicted as orange links on this diagram. Oh no, those are not. But so basically, you're overlaying MAC in IP tunnels onto your physical network, onto your switch fabric. And that's the way you are achieving multi-tenancy. You basically are using the header that you get with, in this case, with a VXLAN to communicate the ID of the tenant. So basically, that's the encapsulation header. And that allows you to have like a full isolation and overlapping IP space support. And then you use software layers to implement routing and switching operations within and across the tenants. So that is basically what allows all SDN vendors that use overlays to operate, because you can implement your own network functionality and software. And then your network world kind of completely changes. You are able to do all sorts of good things, not just rely on some vendors specifications. So and then the quick word on Neutron plugins. There are two different things about a plugin. They're like core APIs that you can implement, if you want to create a plugin. And the core APIs, they basically implement layer 2, those are switch APIs, and then you also get API extensions. And in the bottom part of the diagram, you see how Neutron server will pass through to the plugin, hence the backend, any API calls that create, modify, or remove a network topology. So it's like a problem with the Nova network was the fact that it was monolithic. So if something went wrong, your whole network will go down. Well, here you would be able to mitigate stuff, because it's not it's a completely modular system, right? So there are like two types of plugins in Neutron. You get core plugin, and then you get service plugins. Like The core plugins can be either monolithic, which are plugins that implement like the whole networking backend, and it can the core plugins can also be modular layer 2 plugins, which basically are meant to allow like many different plugins, many different layers. So basically, they allow you to use many different ones to achieve different parts of your functionality. Like, and then there are service plugins that those are your typical X as a service. Like, hey, those are the load balancer as a service, or firewall or VPN as a service. Of these, like a quick, I've noticed, like, I haven't been doing this for a while. Service, like load balancer is like one of the most asked for features in, deploying OpenStack. So if you guys, want to, provide service as a DevOps engineer, you should really know your load balancer and how they interact. Let's see. So the core actually plugins are the ones that do implement L2 APIs. And also quick words on the ML2. So basically, out of the box with most of the OpenStack distributions, you will get OVS, Open vSwitch, and ML2 as an ML2 plugin. People usually think that this is the default, but it's not. You can also use a monolithic plugin that will allow you to have like a complete solution. Yeah, the word is kind of bad, but it's actually very useful thing where you get your whole backend implemented as a single plugin. Quickly about some challenges that you will get if you were to use the default OVS plus ML2 with no ML2. So the challenges that you would face, if you were to use the default stuff, is your service plugins will want to run on separate dedicated network nodes. Placement of of these components on those nodes is like critical, because basically that's in your data path. So if you wanted to have like a, let's say, a LBAS, if it's not sitting in the right path, if it's not like one of the first things that you hit, you'll run into problems. Packets will be punted and all sorts of crazy stuff will be happening. And that is something that will limit your HA, your high availability. Also, when you create new tenants in your cloud, you have to be very careful, and you have to basically size the size of your deployments. If you create too many in the wrong zone, you may just starve your network resources. Depending on your back and implementation, behind Neutron, your packets may be traversing from the kernel into user space, or they will have to go, travel across the network to your network nodes and then come back. So you get very unpredictable sort of network performance when you do that. So let's see. So this is where SDN vendors like my company come into play. We basically are able to provide in our case, a overlay-based networking topology that takes care of all of that. Please excuse the noise. My neighbors are doing something. So with that said, let's look into what's required for high availability. This is like general sort of theory topic that I would like to cover, and that will also, lead into the exact things that we do, the exact things that we have that are used to achieve it. So first of all, regarding network migration, as data centers evolve and people bring in OpenStack or even other cloud management systems into the data center, there's a trend one can see of moving from physical infrastructure to virtual networking infrastructure. People, instead of relying, on their hardware vendors, start processing and start working a lot more with virtualized networks. And this sort of situation warrants, properties of those two worlds that are, when you have like physical networking infrastructure, your quality of service, bandwidth, and latency are, very important. And you also get to do multicast in your physical network infrastructure. You get to plan your capacity and, manage it. And, your connectivity is where it's implemented. With virtual networking infrastructure, you get to do on-demand and multi-tenant networking. Guys, I'm sorry, I'll be right back. The noise here is very, very loud. I'll be right back. I'm sorry about that. Sorry about that. Okay. So, when we look at the hardware that's used in data center networks, like the requirements that we have are pretty well known. They've been around, for a long time, and you guys probably know that, you would have to have reliable hardware. You have to have redundant components. If something goes down, you're expecting a nonstop service, and you would have a rapid failure detection. Like if something goes wrong, you would know that this happened like immediately, and you would also have rapid convergence. I'm probably just repeating something that has been known for quite a while. Now, what is, important for us is what do we require for the same thing in the virtual network world. So in the virtual networking, you would need to have a self-healing network controller. So a self-healing network controller will be basically implemented, and it will operate in active-active configuration. So if something goes wrong, it can very, very easily and very quickly fail over. You will need to have self-healing. So, if, a node goes down, you would know how to get back itself, into operation, and it has to be scalable. So this is something concerning your control plane. Regarding your data plane, you need to have a nonstop forwarding. What that means is your data plane should continue to function. If something goes wrong if your control plane, if the brains of your operation goes down, if your data plane, basically your data plane needs to keep forwarding packets. And you also have to have the ability to do an in-service software upgrade. For those of you that have dealt with Cisco before, that's like a really big selling point. The ability to on the go update your software in your switch and not lose, not drop any packets. The third one is the active-active VTEP gateway. So your gateways that you deploy as the termination point in your overlay-based network, they should be deployed obviously in active-active mode, and they should not need any manual intervention if a failure happens. So, and actually those three things are the first three things are the features that I'm going to demonstrate in a bit. How if your controller goes down, or if your gateway goes down, how you are able to actually survive that event. And the fourth one has to do with your cloud management system, how its failure model is integrated with you. It's basically a feature of the CMS. The other thing is network state should be recreated upon failure or migration event. And obviously rapid detection and convergence is, again, a function of the CMS. It should be able to alert you, like send you a text or something like that. Those are the requirements for virtual networking infrastructure, high availability. And earlier I was talking about, the migration that we've observed going from physical to virtual. When people have working OpenStack with virtual networking deployed in their data center, when you combine those requirements basically for your high availability, you get kind of this picture where your physical networking hardware is expected to like take care of connectivity, have rapid failure detection and rapid convergence. Those are the only things, because all of the wonderful, self-healing and surviving things features are expected to happen on the software side of things, on the virtual infrastructure, basically. So the reliable controller, self-healing, non-stop forwarding, all these can be implemented in software easily. So I'm assuming you guys see how, like, when you have a software, when you have a virtual, network, you can just like expect your physical hardware to, be solid and working, and then have all those expectations of your virtualized network to be all robust and, to survive all sorts of, crazy things. So we are actually running. I'm talking a little bit too much, so I'm going to speed up through the next. So how we achieve high availability. First of all, speaking of Plum Grid, our way of doing things is like we have a separation of control and data plane. So like all of the management, all of the brains of the operations are separate from the forwarding plane, from the data plane. We do have an active-active VXLAN termination endpoint, and we do integrate with the CMS. So I am just going to fly through those slides because they basically say, they basically explain how it's done. I can just give you the gist of it. Our Plum Grid directors is the brains of our operation. That's our control plane. They're based on a distributed hash table, which means that our state, like if something goes wrong on one or one or two of the directors, we have basically an algorithm that will keep the state and transfer it over to whichever node is still available, or it can keep the node in a degraded state. But the main point here is that that allows us to maintain state even with failures. And that also allows for self-healing, obviously. So, and it is definitely built for large-scale deployments, for large resident deployments. The non-stop forwarding. So we have something called virtual domains, which loosely is the equivalent of tenants. Like all of the data is distributed across all of your, compute nodes in this case, via an IOVisor product. I have to mention IOVisor. It's an open source project. It's iovisor.org that basically is an in-kernel. So we are integrated into the kernel, Linux kernel, and our product basically allows for that forwarding, that data plane forwarding. So all of your operations are in kernel, meaning it's like super fast. It can do all sorts of things. And since it's in kernel, our in-service software upgrade is a no-brainer. And not only that, but it does allow us to upgrade like any sort of network function that you are using. You can upgrade it and not lose connectivity. Like most of the other products that are based around like stuff in the user space, you will have to shut down everything, upgrade, and then bring it back up. With us, you just upgrade it, and that's it. Okay. Oh, and this is like the other thing I'm gonna demo. This is our gateway, VTEP gateway. So very quickly, in my setup, I have 2 machines with 2 NICs on each machine. Those NICs are plugged. Each machine has 2 of them going into an Arista switch. The other one has another 2 NICs going into another Arista switch. The Arista switch is configured into an MLAC between the 2. So you have like a complete MLAC high available gateway. A quick, note from the field, so to speak. If you implement a solution like this, you usually want your gateway machine to be like a really beefy one, because like all of your packets going in and out of to the real world, to the physical world, will go through it. So you don't want any sort of surprises there. And obviously, you're on the physical side of things. Your switches are also important. Okay, so and also, another thing is we do allow, like our product allows for a third-party VTEP gateway to, like it allows us to use third-party VTEP gateways as well. All right, so I'm just going to skip over that. Yeah, we work with OpenStack, right? All right, so quickly, demonstration. All right, so, all right, sure. So this is the UI of our platform. I'm not sure if you guys haven't seen it. This is what it looks like. And this is, I've just logged into my OpenStack. All right. Okay. So what I'm going to do is I'm going to quickly create an external network in OpenStack. I am going to tell the PlumGrid platform to use a port bundle as the front of the gateway of our gateway, and then I'm going to demonstrate how if you kill one of your gateways, your packets will still keep going, and also how if you kill your controllers, your data plane will survive and will still be forwarding packets. Okay, so let's quickly create a network, a public network. So I'm going to call it demo. I'm going to use marketing. Let's make it a VLAN one. This is where you specify your host and the name of your NIC that has a VTEP gateway on. And in my physical network, I've provisioned VLAN 5 to be my external network VLAN. I'll create the network very quickly. How to submit to it. Let's put it on 10.5. And this is the gateway on my network switch part. I'm going to tell it to have 10.5.0.100 to 10.5.0.200. So this is the range where my floating IPs are going to live. Okay, so I've created my external network, so I'm going to log into our PlumGrid UI and tell my platform to actually use a port bundle. Port bundle is basically the equivalent of a bond in the physical world. So I'm going to create a connector. I'm going to create a connector. So my it's going to be an LICP connection to the Arista switches that I was talking about. It's a tagged VLAN. If you guys remember, it was VLAN 5. And I'm going to put those two interfaces into it, and then to VLAN 5. Okay. So now, if we say this, VLAN 5 will be available. I'm going to connect VLAN 5 to my public network, pub demo. So that basically ensures that traffic on VLAN 5 is going to be going on the external network. All right. So let's switch to marketing. Quickly, I'm going to create, let's call it web, and I'm going to create a quick subnet, 168, let's say 105, 024. It's going to be web sub. I'm going to enable DHCP. So now I have my public network and I have my, cloud internal network. So I want to bridge those two. I'm going to route between those two. So I'm going to create a demo router, and external network is going to be this. We'll also place an interface on the web network. Okay. Okay, so let's create a VM and place it into the web network. So let's call that demo VM1. Okay, source, come from an image, place it in the web. All right. I'll create one more. Two. Also be on the web. All right. This failed. Okay. So one thing I'm going to do is I'm going to quickly instance this. So this is I have two availability zones, H0 and H6. I'm going to launch the other one into H6 just to demonstrate that it can be running on physically different box, but you would still get the same functionality thanks to a software-defined networking running, behind the scenes. So while this is building, I am going to associate the floating IP with the first. Okay, create one public demo. Okay, associate. All right. Okay. Okay, so we have two VMs on a web network that is routed into our public network, right? So I'm going to launch the consoles. Even just one of the consoles will be good. All right, so actually that's all right. So this one, let's do this. I'm going to launch it to all right, so here I'm going to start pinging my external gateway for my public network. So I'll do 10.501. Okay, it's pinging, good. And here I'm going to start pinging the other VM, which is 192.168.105.4. Okay, so here we see something going outside of the virtual world, and this is a flow of packets within the virtual world. So if I log in, so the first thing I'm going to show is what if one of the NICs on my gateway fails? What's going to happen? So this is going to show the VTIP, the A/A VTIP scenario. So this is, I'm logged into my gateway. So my network card that implements, oh, it's 9. I'm sorry. So I'm just going to finish this really quickly. Okay. So it's on H4, B116P1. So if I'm to turn off the IP, so if I do down P116P1, P116P1, okay, it's disconnected. So as you can see, the data plane is still working. Like one of our gateways is down, but our data plane is still working. So it's down. Let's bring it back up. And now quickly for the other test, let's do, I am logged into the 3 controllers that comprise my OpenStack, and on each one of them we have director service running, which is our control plane. So if I am to if I'm to go for launch, okay. So quickly, I can just stop the director. I can just say service stop. Okay. Service grid stop. Service grid stop. So now I've effectively killed all directors. That is demonstrating the second point, which is if your control plane is down, will your data forwarding still work? And it is working. So basically that concludes the demo. I show how VTAP gateway can be shut down, and you will not lose any networking, and I've shown how you can lose all of your control plane, all of your directors that comprises of your control plane, and your data forwarding will still be working. So we are out of time. Sorry about that. And that's like as a quick wrap up. Having an SDN as a backend will allow you to have a huge amount of flexibility and will be much easier to achieve high availability if your failover and your control and data plane are separated. So we can definitely take questions by email. Sorry about the running out of time part.
Yeah, so we're 3 minutes over, but we want to thank everyone for the time, for being with us today. You can go ahead if you have any questions. You can respond to the email that we sent to you, events@plumgrid.com. Happy to answer any questions you might have. Also, stay tuned. We do a lot more webinars as well as meetups and community events, and we'll be at the Austin Summit and have 7 speaking sessions. So if you're there, definitely stop by. And again, we appreciate your time, and if there's anything we can do for you guys, please don't hesitate to reach out. Thanks, Julian.
Thank you.